This is Edexcel A-level Mathematics, Paper 1, Pure Mathematics 1 from the 5th of June 2019. Question 1 says f of x equals 3x cubed plus 2ax squared, take 4x plus 5a. Given that x plus 3 is a factor of f of x, find the value of the constant a. So here we can use the factor theorem to say that if x plus 3 is a factor, then f of negative 3 must equal 0. So plugging negative 3 into this function, we'll have 3 multiplied by negative 3 cubed, that is negative 27, plus 2a multiplied by negative 3 squared, which is 9, and then we'll have negative 4 times negative 3, which is positive 12, plus 5a, and this equals 0. Simplifying this, negative 27 times 3 is negative 81, 2 times 9 is 18, so this will be plus 18a, plus 12 plus 5a equals 0. And then combining like terms, negative 81 plus 12, that's negative 69. And then 18a plus 5a is 23a. This equals 0. And then we'll have a equal to 69 divided by 23. And then 69 divided by 23, well, 23 goes into 69 3 times. So a is going to equal 3. So final answer there for question 1, 3, for a total of 3 marks. On to question 2 then. Question 2 gives us a diagram. It says figure 1 shows a plot of part of the curve with equation y equals cosine of x, where x is measured in radians. Diagram 1 on the opposite page is a copy of figure 1. Part A says use diagram 1 to show why the equation cosine of x take 2x take a half equals 0 has only one real root, giving a reason for your answer. The first thing to say here, I guess, is that if it only has one real root, that means it only has one solution for this equation. So there's only going to be one possible x value that satisfies this equation. And the way we can do this is to rearrange this equation so that we'll have cosine of x equal to all of this on the right hand side. So let's get started on A then. For A, I'm going to rewrite this equation as cosine of x equal to 2x plus a half. So I've added that 2x and that negative half onto the right hand side. So now I have the cosine graph equal to a straight line graph. Hopefully you can see where this is going. On this diagram then, I can draw in 2x plus a half, and where they intersect will be the solution to this equation. So I want to draw the line of 2x plus a half, or the y-intercept is a half, and I know this must be 1 because this is the graph of the cosine function. They tell you that in the question. It's the graph of y equals cosine of x. So this is going to be at 1, the maximum value of the cosine function, and so this is a half here. And my line has a gradient of 2, so I can go up 2, and this also must be 1 because this is in radians. You can see from the graph, so this will be 1 here. So if I go up 2 and across 1, I'll have another point on that line, and then I can draw my line in. And oops, that's a bad line. Let me do that again. Okay, and then you can see, let's say this is y equals 2x plus a half. You can see there's clearly only going to be one point where this line and the graph of the cosine of x intersect. So we can say graphically that is the reason why it only has one real root. So let's firstly say the root is where the graph and the line intersect. So the root is where cosine of x intersects with 2x plus a half, and we can say from diagram 1, this only occurs once. From diagram 1, this only occurs once. Okay, there we go. That is part A for 2 marks. Part B says, given that the root of the equation is alpha and that alpha is small, use the small angle approximation for cosine of x to estimate the value of alpha to 3 decimal places. For this, you need to know the small angle approximation for the cosine function. This is in your formula booklet, so you don't need to memorize it, but I'll just write it down here. So the small angle approximation for cosine of x is 1 take x squared on 2. So what we're going to do is plug that in for cosine of x in this equation and then solve for x. So we'll have 1 take x squared on 2 equal to 2x plus a half. And now I want to rearrange this in terms of x. So multiply through by 2 to take x squared equals 4x plus 1. And then, well, however you want to do this, I would add x squared to the other side. So then I have x squared plus 4x plus 1 take 2 would be negative 1. And this equals 0. Now I have a quadratic equal to 0 that I don't think I can factorize. So I'm going to use completing the square on this. So half of 4 is 2. So I'll have x plus 2 all squared. And then subtract 2 squared from 1, so we'll have negative 5 equal to 0. And then write this in terms of x, so add 5 to the other side, take the square root, x will be positive or negative, square root 5, take 2. So they are my solutions for x there, assuming that we have a small angle. So we have two possible values for alpha here. Let's look at the graph again. Clearly this solution must be a positive solution. It's in the positive x area of the graph. So if we look at these two solutions, then it can't be negative root 5 take 2. Okay, so we're going to say then that alpha must then equal positive root 5 take 2. And the question said give the value of alpha to 3 decimal places, so we want to plug this into a calculator. The square root of 5 take 2, and I get 0.236 approximately. 0.236 for alpha. Okay, there you go. That is question 2 for a total of 5 marks. Question 3 says y equals 5x squared plus 10x over x plus 1 all squared. Show that dy and dx equals a over x plus 1 to the power n, where a and n are constants to be found. So I'm going to use the quotient rule for this because we have an algebraic fraction. So the quotient rule says that if we have the derivative of f on g, this is equal to the derivative of f times g, take f times the derivative of g all over g squared. And that's in your formula booklet as well. So we can use the power rule on the numerator. This would be 10x plus 10 multiplied by g, which is just x plus 1 squared. Subtract f as it is, so 5x squared plus 10x multiplied by the derivative of g. And using the chain rule, this would be 2x plus 1 multiplied by the derivative of x plus 1, which is just 1, so this would just be 2 times x plus 1. And then this is all over g squared, which would be x plus 1 to the power 4. And then let's start expanding and simplifying. So this would be 10x plus 10 multiplied by x squared plus 2x plus 1. Subtract. Let's actually expand these double brackets out. This would be 2x plus 2. And then expanding that here using FOIL first, 10x cubed. Outers would be 10x squared, inners 20x, and 20x squared, last 10x times 2, 20x. Okay, and this is still all over x plus 1 to the power 4. Okay, let's keep simplifying. So expanding these ones out, 10x times x squared is, well, we probably don't need the brackets anymore actually. 10x cubed. 10x times 2x is 20x squared. And 10x times 1 is 10x. And then 10 times x squared, 10x squared. 10 times 2x, 20x. And 10 times 1 is 10. And then distribute that negative to all of those terms. Also, I could combine those two terms there. So this would be negative 10x cubed. Subtract 30x squared. Take 20x. All over x plus 1 to the power 4. And let's see what cancels here. So 10x cubed would cancel with negative 10x cubed. 20x squared plus 10x squared is positive 30x squared, and we've got a negative 30x squared, so they would all cancel out. And I have a positive 20x here and a negative 20x there. So all I'm left with in the numerator then is 10x plus 10 all over x plus 1 to the power 4. If I factorize 10 out of that numerator, it would be 10 multiplied by x plus 1 all over x plus 1 to the power 4, and that would cancel with one of the x plus 1's on the bottom line. So then I'm left with 10 over x plus 1 to the power 3. So a then is 10 and n is 3. Part B says, hence deduce the range of values for x for which dy on dx is less than 0. Okay, for part B, if dy on dx is less than 0, then all of this is less than 0. So 10 on x plus 1 cubed is less than 0. For this expression to be less than 0, the denominator would have to be a negative, right? Because the numerator is positive. So x plus 1 cubed must be less than 0. And how would this be less than 0? Well, the expression in the brackets would have to be less than 0. Right, so a negative number cubed is still a negative. So if x plus 1 is less than 0, then x is less than negative 1. So to answer the question, the range of values for x, well, that's it, x less than negative 1. Okay, on to question 4. That was question 3 for 5 marks, by the way. Question 4, find the first 3 terms in ascending powers of x for the binomial expansion of 1 on root 4 take x, giving each coefficient in its simplest form. Okay, let's firstly write down the formula for a binomial expansion. So this says 1 plus x to the power n equals 1 plus anx plus half times n take 1 multiplied by ax squared. And they're the first 3 terms. This does go on, but we only have to worry about the first 3 terms. A will be the coefficient of x, so I should have written this as ax plus ax. And that is in your formula booklet as well, so if you can't remember it, you can always check that in the formula booklet. But now we need this expression, 1 on root 4 take x, in this form, 1 plus ax. So let's go ahead and see if we can simplify that down into this form. So the first thing I would do is write it slightly differently. So the square root of 4 take x can be written as 4 take x to the power of a half. If it's 1 over this, it would be 4 take x to the power of negative a half. And then I want this first number to be a 1, so I could factorize a 4 out of that. So this would be 4 multiplied by 1 take. Now, negative x, if I factorize a 4 from that, I'd be left with a quarter x. So negative a quarter x. And all of this is still to the power of negative a half. So I've done that. I've created another set of brackets within those. And then if I expand that negative a half to both of those, 4 to the power of negative a half, that's like 1 on root 4, which is a half. And then these brackets then would be to the power of negative a half. Okay, so we've now got this part of this expression in this form, 1 plus or minus ax to the power of n. So I'm going to perform this binomial expansion on this part of this expression and then multiply it by a half at the end. Okay, so expanding this out then, we have 1 take a quarter x to the power of negative a half equal to 1 plus a and x. A is negative a quarter. N is negative a half. And x is just x. And then we've got plus a half times n is negative a half times n take 1. Negative a half take 1 is negative 3 on 2. And ax squared on the end there. So negative a quarter x all squared. Okay, let's go ahead and see if we can simplify this. Well, we've got 1, a quarter times a half is 1/8, and those negatives would cancel, so we'd have 1/8 x. Here, looking at these denominators, we would have 8 as the denominator and 3 as the numerator. And a quarter x squared, well, the negative would cancel, same with these ones. And this would be x on 16, x squared on 16. And further simplifying this, well, those first terms are fine, but this one would be 3x squared, 16 times 8, that's 128. Okay. I performed that expansion on that part of the expression. Now I need to go ahead and multiply all of this by a half. I'm not sure what that line is there. Okay, so then we can say that 1 over the square root of 4 take x is equal to a half multiplied by this. So 1 plus 1/8 x plus 3x squared on 128. And if I expand that half, we get a half plus 1/16 x plus 3 on 128 times 2 is 256 x squared. So they are my first three terms of my expansion in their simplest form. Part B says the expansion can be used to find an approximation to root 2. Possible values of x that could be substituted into this expansion are x equal to negative 14, because 1 on square root of 4 take x equals 1 on the square root of 18 equal to root 2 on 6, okay? X equal to 2, because 1 on root 4 take x is 1 on root 2, which is root 2 on 2, or x equal to negative a half, because this would simplify to root 2 on 3. Without evaluating your expansion, state giving a reason which of the three values of x should not be used. And part 2 says state giving a reason which of the three values of x would lead to the most accurate approximation to root 2. Okay, this is getting at using validity or a test of validity on your expansion. So a validity test is looking at ax, this term here in this expression, and I might use a different color for that, and we want that number, when we substitute something for x, we want that number to be between -1 and 1. This is to do with convergence. So the idea behind this expansion is that it converges on a particular number. So if we take a value for x, substitute it into this, we want it to be between -1 and 1. So for B, we're going to do a validity test on these values of x. So going back to the question again, well, I'm thinking 14 is not going to give us a value here between -1 and 1. So if we take, well, firstly, let's state what this test is. We want ax to be between -1 and 1. So if x equals -14, ax is equal to -1/4 times -14. This is 14 on 4, 7 on 2, 3.5. This is not between -1 and 1. So x equal to -14 is invalid. And looking at this ax, we would want, well, if we're multiplying x by 1/4 or -1/4, then we would want the absolute value of x to be less than 4 to get a number between -1 and 1. So we could say those are the only valid solutions. Okay, then, so that was part 1. Part 2 said which of these would give the lead to the most accurate approximation. So let's try them both. Let's try 2. So what would we have for ax when, so if x equals 2, ax equals -1/4 times 2. This is -1/2. And if x equal to -1/2, ax equals -1/4 times -1/2. This is 1/8. Okay, so now we're looking for the ax value that is closest to 0. So supposedly that means that your answer will converge closer to the value that you're looking for. So we're going to pick x equal to -1/2 as then -1/4x is closest to 0. Okay, so that was part B. Part 2. And that question 4 was 6 marks in total. Question 5, it says f of x equals 2x squared plus 4x plus 9. Part A says write f of x in the form ax plus b all squared plus c, where a, b, and c are integers. Okay, so we need to complete the square on this. For part A, well, let's write out that function, and then I can scroll down a bit. Okay, so completing the square on this, firstly, I would want to factorize a 2 out of that. So this would be 2 times x squared plus 2x plus 9 on 2. And then complete the square on this expression inside the brackets. This would be x plus 1 all squared. And then subtract 1. So 9 on 2 take 1 is 7 on 2. So positive 7 on 2. And then expand the 2 out again. We'd have 2 times x plus 1 all squared plus 7. Part B says sketch the curve with equation y equals f of x showing any points of intersection with the coordinate axes and the coordinates of any turning point. Okay, well, we know the turning point already from completing the square. That gives us the vertex. And we also know the y-intercept would be 9. And I guess we can find the x-intercepts if there are any. Okay, so actually let's go ahead and sketch this. Firstly, drawing up my axes and my scale. Okay, so these are my axes. I noted that the y-intercept was 9, so I went up a bit. I changed the scale a bit on the y-axis. So let's go ahead and look at the vertex for part B. Well, reading from this equation, it's going to be -1, 7. So that is in vertex form. So just reading the point straight from this equation. As I said before, the y-intercept is equal to 9, or actually I should write the coordinates, 0, 9. And as this is a positive quadratic, and the vertex is a positive y value, then it's not going to have any x-intercepts. So let's just go ahead and write it and you'll see what I mean. So the vertex -1, 7. So -1 was here. 7 would be about here. Y-intercept is at 9. And, well, we would have another point then at -2, 9. So you can see here there are not going to be any x-intercepts. So let's go ahead and sketch this in. I'm not going to bother finding any other points. I'm just going to see if I can get an approximate shape. And because they don't ask you to show any other points on this graph, they just ask you to show the y-intercept and the vertex. And that should be good. So let's write in the function, or actually let's say y equals, what was it, 2x squared plus 4x plus 9. Okay, so that should be good enough for my sketch. Part C says describe fully the transformation that maps the curve with equation y equals f of x onto the curve with equation y equals g of x, where g of x equals 2 times x take 2 all squared plus 4x take 3. Looking at this expression, it's not immediately obvious how it's been transformed from 2x squared plus 4x plus 9, but there's a little trick you can use here to show what has occurred. And let me go ahead and show you what that is. So let's write that down below for g of x. Let's do it down here. So for part C, part 1, we've got g of x equal to 2 times x take 2 all squared plus 4x take 3. And we're comparing this to f of x, which was 2x squared plus 4x plus 9. Now, this would be a little bit easier if this bit here was also x take 2, because then we could say, well, they've just changed the input from x to x take 2, and I know what transformation that creates. That is a transformation to translation to the right 2 units. So what if I just do that? What if I put x take 2 in here instead of x? Well, let's see. So leaving this first term as is, let's substitute x take 2 in here. So now my inputs are the same, but what happens here? What have I added? Well, I've still got a 4x. If I expanded this out, I'd still have 4x, but then I'd also have a negative 8. So I've kind of added a negative 8. So what can I do to counteract that negative 8? Well, I could add a negative 8. So I could add negative 8 to this. Sorry, I could add 8 to this expression. So negative 3 plus 8 would be plus 5. Okay, so now these two things are equivalent. These two expressions, and I have that input of x take 2. Okay, so what does this mean? Well, we have x take 2 is the input. That means, well, if you know about graph transformations, if you change the input to x take 2, you will have a translation to the right 2 units. And I've also changed the y-intercept from plus 9 to plus 5. Actually, we should check that. So if x equaled 0, we would have 2 times 4, and then 2 times 4 plus 4 times negative 2 plus 5. So yeah, you can see this 8 would cancel with this negative 8. So this equals 5. So we have a y-intercept of 0, 5 and a translation to the right 2 units. So in total, we have a translation of 2 and negative 4. So it's gone from a y-intercept of 9 to 5. So that's a translation down 4 units. And there's been no other transformation of the graph because these coefficients are still the same. We still have 2 x take 2 squared plus 4. Okay, so the only transformation that we've done is a translation. So there's a little bit of a trick there for part C1. And then part 2 says find the range of the function h of x. Well, hopefully you notice that we have f of x down here in this denominator. This is the same as the function we had in part A, f of x, 2x squared plus 4x plus 9. And we have graphed that, and we have a range for f of x. So we could start off with that for part 2. H of x equals 21 on f of x. And the range of f of x, well, let's look at the graph again just to remind ourselves. The minimum was 7, the max is infinity. So the range then is 7 to infinity, and that's equal to. So looking at this expression, we have a minimum of 21 on infinity. That would give us basically 0, right? Any number over infinity will be almost 0. So we can say that the range of h of x is greater than 0, not quite equal to 0, but greater than 0. And it's going to be less than or equal to, because this was greater than or equal to, 21 on 7, which is 3. Okay, so that is my range, 0 to 3. And that was for 2 marks. Part 1 was also 2 marks. Total of 10 marks for question 5. On to question 6. Part A says solve for negative 180 to 180. The equation 5 sine 2 theta equals 9 tan theta. Give me your answers where necessary to 1 decimal place. And solutions based entirely on graphical or numerical methods are not acceptable. Okay. Alright, so we have 2 theta here. So I want to get rid of that first. So using the double angle formulas, which are in your formula booklet, let's start with that. Let's say a sine of 2 theta is equal to 2 sine theta cosine theta. And this is equal to 9 tan theta. Actually, let's rewrite this as well to sine theta over cosine theta. And let's see if we can rearrange this to solve for theta. Well, the first thing I would do here is divide through by sine theta. They disappear or cancel each other out. And then multiply on this side by cosine theta. So I have cosine squared theta. this is equal to, well, this was 10. 5 times 2 is 10. Divided by 10 on this side, I've got 9 on 10. And then take the square root. So we would have cosine theta of plus or minus 3 on square root 10. And then theta is equal to the inverse cosine of plus or minus 3 on root 10. Okay, so I have an expression for theta, and this is going to give me a reference angle. Now you can use the unit circle to help you with these types of questions, because that's going to show you where or what angles to look at. So, well, we've got a positive or negative value here for cosine theta. That means that we're going to be looking at this value in all 4 quadrants. Excuse me, I just want to move this line across. There we go, that's a bit better. We've got an angle in all 4 quadrants because cosine of theta is positive and negative in all 4. So we'll have, well, firstly, let's find this reference angle. And then let's look at the angles we're going to be looking for. So the inverse cosine, and I'm working in degrees here. They give me the range or the domain in degrees. So we want our calculators to be in degrees. And then we want the inverse cosine of 3 on root 10. And I get 18.43. So that's the positive value. So cosine of theta is positive in these quadrants. And as I said, this is our reference angle. So this would be 18.43 in here and also down here. Okay. All right, so they are 2 of our answers. And because we're going from our domain is negative 180 to 180, then this will be a negative angle. We're not going all the way around. So we're just going from 0 to 180 and 0 to negative 180. So this would be negative 18.43 and 18.43. There are 2 answers. We also need to do negative, the inverse cosine of negative 3 on root 10, which is essentially will be 180 take this angle, but well, you know, you can do it either way. But let's do negative, the inverse cosine of negative 3 on root 10. And this will give us 161.56. Now, did it say to round off to 1 decimal place? Okay. All right, so, well, this is going to be 161.6. And again, this is either in the second quadrant, or the third quadrant. Okay, so the angle that we're talking about here is all the way around. So that's going to be 161, whatever it was, and this one's going to be negative 161. So we have some answers for theta. Theta is equal to 18.4 degrees, or negative 18.4 degrees, or what was that number again? 161.6 degrees, or negative 161.6 degrees. And there's also some other values that we have to remember. So if theta was 0, this equation would still hold as well, or this original one. So sine of 0 is 0. So we just have 0 equal to 0, which works as well. Same for 180. So we actually have some other solutions here. We have 0 and we have plus or minus 180 degrees. So because they tell us in that domain, theta is greater than or equal to negative 180 and less than or equal to 180. Okay, so make sure you include those values there. And in total, we get 7 solutions for 6 marks for part A. Part B says deduce the smallest possible solution to the equation 5 sine 2x take 50 equals 9 tan x take 25. Okay, so for this one, we have the solutions to this equation, and we need to set them equal to 2x take 50 and see what would give us the smallest positive solution for x. So we can say theta equals 2x take 50. theta equals x take 25. So 2 theta equals 2x take 50. Theta equals x take 25. So what would give us the smallest value for x here? What value for theta? Well, let's say x take 25 is equal to, well, if it equaled 18.4, we would add 25 to it and we would have, 40 something. What about negative 18.4? That would still give us a positive value, right? Because we'd be adding 25 to it. But could we get a smaller positive value? Well, 0 would give us positive 25. Negative 161 would not give us a positive value. So yes, it's going to be when theta equals negative 18.4. And then x is going to equal negative 18.4 plus 25. Let's just put that into a calculator. And I get 6.6 for x, 6.6 degrees. And just double checking, I answered the question, deduce the smallest possible solution for the equation. Yes. So x equal to 6.6 degrees for that one. That was a total of 8 marks for question 6. On to question 7. Well, question 7 says, in a simple model, the value V pounds of a car depends on its age T in years. The following information is available for car A. Its value when new is £20,000. Its value after 1 year is £16,000. Use an exponential model to form for car A a possible equation linking V with T. Okay, so for part A, well, an exponential model has a general form of V equal to a r to the power T, and they tell us when new, its value is £20,000, so that's when t equals 0. So that means, well, if t is equal to 0, r to the power 0 is 1. So v when t equals 0 is equal to 20,000. So we can straight away say that a is equal to 20,000. And then using this data point, the value after 1 year is 16,000, input that in. So when t is equal to 1, v is equal to 16,000, then we would have 16,000 equal to 20,000 r to the power t. Sorry, t is 1 here. So then r is going to be 16,000 on 20,000, basically 16 on 20, which is 4 on 5. So therefore, the equation for v can be written as 20,000 times 4 on 5 to the power t. For a final equation linking v with t, part B says the value of car A is monitored over a 10-year period. Its value after 10 years is 2,000. Evaluate the reliability of your model in light of this information. Okay, so let's plug in 10 and 2,000. And see what we get. Or sorry, let's just plug in 10 and see what I get for V. Okay, so for part B, when t equals 10, V equals 20,000 multiplied by 4 on 5 to the power 10. Let's put that straight into a calculator. 20,000 multiplied by 4 on 5 to the power 10. And I get 2,147.48 approximately. And I would say that's pretty close. So quite close. So this is approximately 2,000. I would say the model is somewhat reliable. So the model is somewhat reliable. For part B, part C says the following information is available for car B. It has the same value when new as car A. Its value depreciates more slowly than that of car A. Explain how you would adapt the equation found in A so that it could be used to model the value of car B. So if it's depreciating more slowly, well, what impacts the depreciation? It's R, right? So let's say the value of R is smaller. Let's say it's 0.5. After 1 year, we would already have half the value of the car because 0.5 to the power of 1 is 0.5. So 20,000 times 0.5 would be 10,000. So if R goes down, the value is depreciating faster. If R goes up, it's depreciating slower. So looking at this statement, the value depreciates more slowly than that of car A, this value for R needs to increase. So for part C, I would say in my equation, V equals AR to the power T, the value of R would increase. The value of R would increase. And I believe that was just 1 mark. Yes, so that's all I would say for that, for part C. Okay, on to the next question. Question 8 gives us a diagram. And it says figure 2 shows a sketch of part of the curve with equation y equals x times x plus 2 times x take 4. The region R1 shown shaded in figure 2 is bounded by the curve in the negative x-axis. Part A says show that the exact area of R1 is 20 on 3. Okay, so we have an equation here, and they also give us the solutions, right? If this is already factorized, that means x would be 0, so that would be one intercept. This would be -2, and this point here, sorry, not that point there, this point over here would be at 4. Okay, so because it's already factorized, I know the x-intercepts. So this region here is going to be from -2 to 0. So that's going to be the integral I'm looking for. So also I would probably expand this out first before integrating. So I would say for part A, well, firstly, let's say the roots equal -2, 0, 4. And then, so y equals x times x squared, take 2x, take 8. And this is x cubed, take 2x squared, take 8x in expanded form. And then if I was doing the integral of y from -2 to 0, this would be the integral from -2 to 0 of this. So x cubed, take 2x squared, take 8x. And then using the power rule, this would be x to the power 4 on 4, take -2 on 3, x to the power 3, subtract 4, so 8 divided by 2 is 4x squared. And this again is from -2 to 0. And now let's go ahead and plug these in and subtract. So plugging these values in then, we have the upper boundary, subtract the lower boundary, so plugging 0 in, well, all of these terms have an x term, so that would just be 0. Subtract, plugging -2 in, -2 cubed, sorry, -2 to the power 4 is 16 divided by 4 would be 4. Take 2 on 3 times -2 cubed, that would be -8 times -2 would be positive 16 on 3. And -2 squared is 4 times 4 is 16, so that'd be -16. And then simplifying this, we have, well, if we combine all of this, 4 times 3 is 12, plus 16, take 3 times 16 is 48. Take 48 on 3. This is equal to 12 plus 16 is 28. Take 48 is -20. And then expand that negative, we would get positive 20 on 3. So the area of R would be, well, we should have said area R is equal to all of this, so R is equal to 20 on 3. Okay, so that was part A, or R1, sorry, R1. Okay, and part B says the region R2, also shown shaded in figure 2, is bounded by the curve, the positive x-axis, and the line with equation x equals b, where b is a positive constant and 0, and b is between 0 and 4. Given that the area of R1 is equal to the area of R2, verify that b satisfies the equation b plus 2 all squared multiplied by 3b squared, take 20b plus 20 is equal to 0. Okay, so we are saying that R1 equals R2 and we want a value of b. so that those two areas are equal. So for part B then, we are going to take the integral from 0 to b, and we already have the integral of that curve. It was x to the power 4 on 4, take 2 on 3 x cubed, take 4x squared. That's straight from part A, and this is from 0 to b, and the area under the curve is a negative area, so we're going to say it's equal to negative 20 on 3. And then substituting those in, the upper value will be substituted first. This is b to the power 4 on 4, take 2 on 3 b cubed, take 4b squared, take 0, so plugging 0 into this would just get 0, so don't need to worry about that. And then this is all equal to negative 20 on 3, and then we can multiply through by 12 to get rid of all of these denominators. 12 times b to the power 4 on 4 would be 3b to the power 4. This would be 8b cubed, take 4 times 12 is 48, so negative 48b squared equal to negative 20 times 4 would be negative 80, and then simplifying further we would get 3b to the power 4 take 8b cubed, take 48b squared plus 80 equals 0. And now let's go back to the equation we're looking for. We're looking for b plus 2 squared, all squared, multiplied by 3b squared, take 20b plus 20 equals 0. So you could either expand that out, or you could try to factorize this. Either way would be fine here. So I'm going to do that. So starting with b to b plus 2 all squared multiplied by 3b squared, take 20b plus 20. Let's expand this out and see what we get. We would have firstly b squared plus 4b plus 4 multiplied by 3b squared, take 20b plus 20, and then b squared times 3b squared would be 3b to the power 4, b squared times negative 20b, negative 20b cubed, b squared times 20 plus 20, positive 20b squared. 4b times 3b squared is positive 12b squared, 12b cubed. 4b times negative 20b, negative 80b squared. 4b times 20, 80b. 4 times 3b squared plus 12b squared. 4 times negative 20b, negative 80b, and then 4 times 20 plus 80. Okay, so let's simplify further. 3b to the power 4, and then negative 20b cubed plus 12b cubed would be negative 8b cubed. Okay, and then we've got 20b squared, take 80b squared plus 12b squared. That would be negative 80 plus 32b squared. That would be negative 48b squared. And then I believe that's everything. Oh, the b terms, we've got 80b and negative 80b. They would cancel out. We've simplified everything else, and then we've got a plus 80 on the end. Okay, so we can say then that this would factorize. If we go down here, then this would factorize to b plus 2 all squared multiplied by 3b squared, take 20b plus 20 equal to 0. Okay, so that would be how I'm approaching b. Part C says the roots of the equation 3b squared take 20b plus 20 equals 0 are 1.225 and 5.442 to 3 decimal places. The value of b is therefore 1.225 to 3 decimal places. Explain with the aid of the diagram the significance of the root 5.442. Okay, so we've got a value of b. Looking at the diagram, they said b is equal to 1.225, and that's because it's roots of this quadratic here. Now, what's the significance of 5.442? That's a root of this equation as well. Remember what we were trying to solve here. We were trying to solve this integral when it equals the area of 20 on 3, or negative 20 on 3. So the values of b are when this area, or this integral, are equal to negative 20 on 3. So if we get another value for b of 5.442, that's an x value out here somewhere. So let's draw in a line, and then the area of under the curve under these two bits must be equal, right? Because they effectively cancel each other out. So this would be the other value of b, for which these two areas cancel out, and we're still left with this value, or this area of negative 20 on 3 between 0 and b. Okay, so hopefully that makes sense. We're going to say then that these two areas are equivalent. So these two areas are equivalent when b equals 5.442. Again, because they'll cancel each other out, so that you're still left with this area equal to R2. Hopefully that makes sense. Anyways, moving on to question 9. Question 9 says, given that a is greater than b is greater than 0, and that a and b satisfy the equation log a take log b equals log a take b, show that a is equal to b squared on b take 1. Okay, so we could use our log laws. Log a take log b. Log a take log b. Let's just write this out first. Log a take log b is the same as log of a divided by b. So this is log of a take b. So therefore then, those two inputs must be the same. So we can say a on b is equal to a take b. And then we're trying to make a the subject. So multiplied by b would get a equal to ab take b squared. And then combine like terms. So we would get a b take a equal to b squared. So I've flipped it around a little bit there, and then factorising a would get a multiplied by b take 1 equal to b squared, and then a equal to b squared on b take 1. Okay, so the use of log laws and some algebra there for part A. Part B says write down the full restrictions of the value of b, explaining the reason for this restriction. Well, for this expression, b cannot equal 1, right? Because then this would be undefined. So for b cannot equal 1. Also, looking again at this inequality, a greater than b greater than 0, if a is greater than b, and that's greater than 0, then this needs to be greater than 0. So b squared on b take 1 greater than 0. So this is saying this needs to be a positive number. So that means then that this denominator cannot be, or must be greater than 0. It cannot be a negative number. So then b is greater than 1. So to answer the question, write down the full restriction on the value of b. Well, that would be it, b greater than 1. So that's kind of contained within that. B does not equal 1. It's greater than 1. Okay, that was question 9 for 5 marks. Question 10 part 1 says prove that for all n belong to the natural numbers n squared plus 2 is not divisible by 4. For this I'm going to go through two methods. One, proof by contradiction, and the next one will be a bit more straightforward. The first method is what I used when I tried to solve this. The second method is straight from the mark scheme, and in my opinion would be the method I would suggest you use. So the proof by contradiction, well, we're going to firstly assume that n squared plus 2 is divisible by 4. So we say let n squared plus 2 equal 4 multiplied by something, so 4a in this case. And because n is belonging to the natural numbers, a also must be belonging to the natural numbers. So we're assuming that n squared plus 2 is divisible by 4, and then we can say therefore n squared equals 4a take 2, and then n squared is equal to 2 multiplied by 2a take 1. Okay, so just factorizing that right hand side. And now we have n squared equal to 2 multiplied by some number, and that means therefore n squared must be even. So this must be an even number, right? Because it's multiplied by 2. So this is an even number. And let's say, again, let's just state therefore n squared is even. Okay, and then if a squared number is even, we know that its square root must be even. So let's put that into a sentence. If n squared is even, n is even. And my reasoning there would be as an even number multiplied by another even number is an even number. Also, I guess we're relying on the fact that if we multiply an odd and an odd number, so we multiply an odd and an odd number, we get an odd number. So n cannot possibly be odd in this case. So also, if n is even, then n squared must be a multiple of 4, because n then would be a multiple of 2. So that's my next statement. Therefore, n squared is a multiple of 4. And just to show you what I mean, because then we'd have two even numbers multiplied by each other, and we'd get 4 lots of something, 4 lots of k squared in this case. Hence, we have a contradiction, because remember we said n squared plus 2 at the start was a multiple of 4 or divisible by 4. So we have a contradiction. So we would say if n squared is a multiple of 4, n squared plus 2 cannot also be a multiple of 4. If you have a multiple of 4, add 2 to it, it can't also be a multiple of 4. So then let's state this is a contradiction. And this is true for all n, belonging to the natural numbers, I should say. Okay, so that's the first proof by contradiction. Let me go through another method that I think is a little bit more straightforward. It doesn't rely on proof by contradiction, it's a direct algebraic proof. So we can say for this one, this is method 2. This is the one I would suggest you use. We could say let or if n equals 2m, then it follows that n squared plus 2, plug 2m for n, equals 4m squared plus 2. And then we can see this cannot be divided by 4 and give an integer, right? We have a multiple of 4 here. If we add 2 to it, we're not going to get a multiple of 4. So we could state that. So this cannot be divided by 4 and give an integer. That's if n is even. Let's say if n is odd, so 2m plus 1, then we would have n squared plus 2 equal to 2m plus 1 all squared plus 2. Expanding this out, we'd get 4m squared plus 4m plus 1 plus 2 would be 3. And then if you factorize a 4 there, we would have 4 times m squared plus m plus 3. And again, we have this situation where we have a multiple of 4 plus 3. This cannot be a multiple of 4, right? You've taken a number such as 16, added 3 to it. So again, we could use this statement. This also cannot be divided by 4 and give an integer. Okay, so then I guess this is true for all n belonging to the natural numbers. Okay, so 2 methods there. Hopefully you find one of those useful. Okay, part 2. Given x belonging to the real numbers, the value of the absolute value of 3x take 28 is greater than or equal to the value of x take 9. State, giving a reason, if the above statement is always true, sometimes true, or never true. I'm going to use an algebraic proof for this, but you could also do it graphically as well. So for part 2, we have the statement, the absolute value of 3x take 28 is greater than x take 9. Okay, so let's see what values for x this holds. Is it always true, or just sometimes true, or never true? So to get rid of absolute value symbols, we can assume this statement is all positive. So 3x take 28 is greater than x take 9. Then we also have the negative case of this absolute value. So this could be a negative in here. If I'm looking for the value of x, then I want to basically divide by negative 1. So here we would have 3x take 28 and divide this side by negative 1. When we divide by negative, we also have to flip the inequality. So we'd get less than 9 take x, so those signs would change there. Okay, so then we have to solve for x in these two cases. So add 28 to the right hand side, take x, we'd get 2x greater than negative 9 plus 28, that's 19, and then x greater than 19 divided by 2, 9.5. And let's solve this one over here for x. Add 28 to the other side, 28 plus 9, that's 37, and 3x plus x is 4x, less than 37. 37 divided by 4, that would be 9 and a quarter. So x is less than 9.25. Okay, so we have the set of values for x. We have x greater than 9.5 or x less than 9.25. That leaves a gap in there in which x could not be equal to. So x could not be equal to, for example, 9.3. Well, actually, it's only greater than these. So it couldn't actually be equal to 9.5. So let's test to make sure our working out is correct here. Let's say that x did equal 9.5. Let's see what we would get here. So 3 times 9.5, that's 28.5. Take 28 is 0.5. And this needs to be greater than x take 9. 9.5 take 9 is 0.5. So yes, in this case, we would not have an inequality. We would have an equality. So this indeed is correct. Let's try 10 then. So this should work then if x is 10, because it can be greater than 9.5. So we'd get 30 take 28, which is 2. 10 take 9 is 1, okay. And we're also saying it can be less than 9.25. Let's try 9. 3 times 9 is 27. 27 take 28, negative 1, but it's the absolute value, so it'd be 1. And then 9 take 9 would be 0. Okay, so that works in that case. Okay, so I'm fairly confident my workings out is correct there. So I would say this is sometimes true. X is greater than 9.5 and x is less than 9.25. Okay, so that was part 2 of question 10. Part 1 was 4 marks, part 2 was 2 marks. On to question 11. Question 11 says a competitor is running a 20-kilometer race. She runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. After the first 4 kilometers, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometer is modeled to be 5% greater than the time that she took to complete the previous kilometer. Using the model, part A says show that her time to run the first 6 kilometers is estimated to be 36 minutes, 55 seconds. Read this carefully would be my first suggestion. She's run each of the first 4 kilometers at a steady pace of 6 minutes per kilometer, and then she begins to slow down. And we're looking for the first 6 kilometers. The first 4 kilometers, we've got that time basically. It's going to be 24 minutes, 4 times 6. And then the next 2, we need to add 5% on to that time, that's 6 minutes. So I wouldn't suggest any more complicated method here than doing increasing 6 minutes by 5% and adding those on. Okay, so part A, that's what I'm going to do. We've got 24 minutes for the first 4 kilometers plus 6 times 1.05 to increase that by 5%. And then the next one is going to be that multiplied by 1.05 again. So 1.05 squared. So this would be the 5th kilometer. The time increased by 5%, and this will be the 6th kilometer. The time increased by 5% twice. So let's put that into a calculator. We've got 24 plus 6 times 1.05 plus 6 times 1.05 squared. And I get 36.915. And this is in minutes. And the question said, show that a time is estimated to be 36 minutes 55 seconds. So let's just find that 0.915 in seconds. 0.915 multiplied by 60. I get 54.9. Rounded to the nearest second would be 55. So this then I can say rounds off to 36 minutes 55 seconds. Okay, so that was part A. Part B says show that her estimated time in minutes to run the 1/8 kilometer for r between 5 and 20 is 6 times 1.05 to the power of r take 4. For this question, because it's only 1 mark, don't assume that you need some complicated proof. I would suggest writing down the times for each kilometer, or starting with that. So we're looking for the kilometers 5 to 20. So start with the 5th kilometer. How would you express that in an expression such as this? So that would be my thinking on this to start with for B. So I would say the times, let's start with the 5th kilometer. This would be 6 multiplied by 1.05, right? I've already done that in the previous question. And in terms of r, how could I express that in terms of r? R being the rth kilometer. So this was the 5th kilometer, and I've essentially raised this to the power of 1. Well, firstly, let's just say this would be the same as saying 1.05 to the power of 5 take 4. Okay, let's do the 6th kilometer. And again, I did that in the previous question as well. This was 1.05 squared. And we could write that as 6 times 1.05 to the power of 6 take 4. And let's do another one. This would be 6 times 1.05 cubed, which we could also write as 6 times 1.05 to the power of 7 take 4. So I'm basically just looking at this expression and seeing how I can relate the number of kilometers with 4. And then we're seeing for the rth kilometer, we could write this as 6 multiplied by 1.05 to the power of r take 4. Okay, that was part B. Part C says estimate the total time in minutes and seconds that she will take to complete the race. And here I would probably go to the geometric sequences, sum of a geometric sequence, because that's essentially what we have. We're multiplying by the same thing each time. So the total time we could write as an expression of the first 4 kilometers plus the next 16 kilometers as a geometric sum. And one way we can write this as the sum of r from 5 to 20 of 6 times 1.05 to the power of r take 4 minutes. And then let's try to solve this. So this would be equal to, now actually I'm going to write down the formula for a geometric series up here somewhere, I guess. Geometric series, or the sum of a geometric series, and this is in your formula booklet as well on page 5. This is the one I'm talking about here. So this says that the sum of n terms, that shouldn't be an equal sign, the sum of n terms is equal to a, the first term, multiplied by 1 take r to the power n, divided by 1 take r being the ratio between each term. So in this case, a, our first term, would be actually, so if I'm using 6 as my first term, then I would want to go from r equal to 4, because that's the last kilometer it was equal to 6. In this case, I'm going to change this to 18 plus r from 4 to 20. You could also do it as r from 5 and 24 here. In this case, your first term then would be 6 times 1.05. Either way would be fine there. But anyways, let's start plugging these in. As I said, a, the first term, is 6 multiplied by 1 take r to the power n, n being the number of terms. Now, if we go from the 4th kilometer, including the 4th kilometer, that would actually be 17 kilometers. So this r to the power n here is going to be 1.05 to the power of 17. And then this is divided by 1 take 1.05. That's the ratio between each term because we're increasing by 5%. And then after we've done that, we just need to plug that into a calculator. So let's see what we get here. So we've got 6 multiplied by 1 subtract 1.05 to the power of 17. This, I might just do that first and then divide that by 1 take 1.05. That would be negative 0.05. and I get 155, and then I need to add 18. So for all of this, I get 173.04. 173.04. And just going back to the question quickly, it said give the time in minutes and seconds. So this is currently in minutes. If I wanted to round this off to minutes and seconds, then, well, I'd have 173 minutes. And how many seconds? Well, I could subtract 173 from this and then multiply by 60. And I get 2.53 seconds. Rounding that up, I'd get 3 seconds. Okay, so final answer there, 173 minutes and 3 seconds. Not a typical geometric sum question because you had to kind of figure out the number of terms. I think that's a bit tricky, and also the first term. A few little tricky steps there, but hopefully you went okay with that question. Okay, that was question 11 for a total of 7 marks. On to question 12. Question 12 gives us a function f of x equal to 10 multiplied by e to the negative a quarter x sine x, where x is greater than or equal to 0. Show that the x coordinates of the turning points of the curve with equation y equals f of x satisfy the equation tan of x equal to 4. Okay, turning points of a curve, that should tell you a derivative, and when the derivative is 0, because the turning points here in this case are where the gradient of the curve are 0. So we want to take the derivative of the function and set it equal to 0, and then hopefully end up with tan of x equal to 4. So that is where I'm starting for part A. Let's firstly write down this function. We've got 10 e to the negative 0.25x sine x, and we are looking for f prime, or you could write dy and dx, either way. So taking this derivative, I would use the product rule because we have two functions here multiplied together. The product rule says if we're taking the derivative of f times g, this is f prime times g plus f times g prime. And so f prime, well, this is my first function, e to the power of negative 0.25x. In this case, I need to use the chain rule, so multiply by that coefficient of x there. This would be negative a quarter times 10, or 10 on 4, e to the negative 0.25x. And the derivative of e is just itself, so that would be the derivative of the first function. This is multiplied by g as it is, so sine x, and then we add on f, which was 10e to the negative 0.25 multiplied by g prime. The derivative of sine x is cosine x. Okay, so we have that derivative, and then let's go ahead and set this equal to 0. So we have negative 10 on 4e to the negative 0.25x multiplied by sine x plus all of this, oops, I forgot the x there, multiplied by cosine x equals 0. And then we can cancel a bunch of things. So if we divided by e to the power of 0.25x, they would cancel out. Also the 10s would cancel out. So what we're left with here is, I'll go on to the next page, what we're left with here is negative a quarter sine x plus cosine x equal to 0. Then we could add that sine x to the other side, so we'd have cosine x equal to a quarter sine x, and then divide by cosine multiplied by 4 on this side. We would have therefore tan of x equal to 4. So there we go, we've shown that the turning points of the curve satisfy the equation tan x equal to 4. Figure 3 shows a sketch of part of the curve of the equation y equals f of x. Part B says sketch the graph of h against t, where h of t equals the absolute value of 10 e to the power of negative 0.25t sine t, showing the long-term behavior of this curve. So if it's the absolute value, then these negative parts of this curve would just be positive. So rather than going down below the x-axis, we just go like that. So where do I have to sketch this? In I guess down below here somewhere. Oh, they've given us a space. Okay, so let's go ahead and see if we can sketch this somewhat neatly. So we've just got positive values of x and y. So we're talking about h of t equal to the absolute value of all of this. Okay, and well, we can kind of use the sketch they gave us and hopefully do it somewhat neatly, which I can never manage to do on here. But I guess the main thing is that we get the fact that all of the curves are above the x-axis and that they somewhat look like the curve that we already see in the question. And they're going lower and lower. And the intervals then, if we look at this graph actually, we notice that the intervals are all evenly spaced because there's nothing in this function actually that would change those intervals. For y equal to 0 or f of x equal to 0, we would be getting similar values because we're talking about the sine function, which has a set period. Okay, anyways, none of that's really important for this part, but let's try to show the long-term behavior. I guess it's just getting lower and lower and flattening out, and maybe even that could be even flatter, and I guess eventually it would just become almost a flat line. Okay, hopefully that's enough for 2 marks there. Part C says a function h of t is used to model the height in meters of a ball above the ground t seconds after it has been kicked. Using this model, find the maximum height of the ball above the ground between the first and second bounce. Okay, so the maximum height between the first and second bounce, well, okay, let's look at the graph that I sketched. This would be the first bounce, if we're talking about a ball bouncing on the ground. This would be the second bounce. The maximum height would be this turning point, and we have an equation for the values, the x values of the turning points, and I wrote this graph incorrectly. This should be t down here because we're talking about time now for this particular graph. And the question, just going back again, maximum height above the ground. So firstly we could find the value of t of the turning point, the maximum height, and then plug that into h of t. So using tan of t equal to 4 in this case, let's try to solve that. So for part C, we can say that tan of t equal to 4 for the turning points, from part A, and therefore t is going to be the inverse tan of 4. So let's get some values for t now, and we're talking about radians, or actually I don't know if it matters whether you use degrees or radians here because you're looking for h of t, so I think that it doesn't matter, but let's use radians anyway. So the inverse tan of 4 gives me 1.3258 approximately. T is equal to 1.3258, and we also need to include the period of the tan function, which is pi. I should say k pi because it's not just once, it goes on and on. So these would be the solutions for t, and then we want the second solution. So the second solution would be plus pi. So we just need to do it once for the second solution. This would be 1.3258 plus pi, and for that, well, let's take that answer, add pi, and I get 4.467 approximately, 4.467, and then plugging that into the function h of t. So h of 4.467, that's going to be, what was it? The absolute value of 10e to the negative 0.25. This, multiplied by sine of this, and let's see what we get there. 10 multiplied by e to the power of negative 0.25 times the answer, multiplied by sine of the answer. That answer key really helps out, doesn't it? And I get negative 3.17, but we're talking about the absolute value, so it's going to be 3.175. 3.175. And just double checking, well, it doesn't say to round off, but remember the start of the paper says round off to 1 or 2 significant figures, so this is going to be 3.18 meters, because h was in meters. So that would be my answer for part C, the maximum height between the first and second bounce. Part D says, explain why this model should not be used to predict the time of each bounce. The time of each bounce. Okay, so I kind of alluded to this when I was sketching this graph. If you think of a ball bouncing, it's not just the height of the bounces that gets less, it's actually the distance between the bounces gets less, and also the time between the time that the ball hits the ground gets less. So in this case, this model is not going to be accurate because we would be needing to decrease this time between each bounce. So for part D, to answer that question, just go back to the question again, sorry. It should not be used. Why it should not be used? Because the time between each bounce is not decreasing. The time between each bounce, is not decreasing. Okay, and you can elaborate on that as well if you'd like. So that was 1 mark. Total for question 12 was 6, 7, 8, 9, 10 marks. Question 13 says the curve C with equation y equals p take 3x over 2x take q multiplied by x plus 3, where p and q are constants, passes through the point 3.5 and has 2 vertical asymptotes with equations x equals 2 and x equals negative 3. Part A, part 1 says explain why you can deduce that q equals 4. So they tell you there are asymptotes at x equals 2, x equals negative 3. That means the function is undefined at those points. To have a function undefined, you need the denominator to be equal to 0. And we can see clearly here, if x equals negative 3, this expression here would be 0. Negative 3 plus 3 is 0. And for x equal to 2, we would need this one to be equal to 0. So we can start off with that for part A, part 1. We could say when x equals 2, 2x take q equals 0. So therefore 4 take q equals 0. Therefore q must equal 4. And we can add some reasoning there for y to be undefined. Okay, so we get q equal to 4, and then part 2 says show that p equals 15. And for this, we can use this point that they give us on the curve, plug it into y, and then find p. So let's go ahead and write that expression down below for part 2. Well, we just found q equals to 4. So we've got y equal to p take 3x all over 2x take 4 multiplied by x plus 3. And then we could say using the point 3.5, plug that in here, so we'll get 1/2 equal to p take 3 times 3 is 9, all over 2 times 3 is 6, take 4 is 2, 2 in that first bracket, and then 3 plus 3 is 6 in the second bracket. And then keep simplifying that algebra. Well, this would be 1 if we multiply by 2, and then p take 9 equal to 6, p take 9 equal to 6, and then therefore p is equal to 15. Okay, please don't take this level of neatness to be acceptable. Please set your work out correctly. I apologize, but I'm trying to go a bit faster here. So that was part A. Now part B, is, you'll note an 8-mark question. We're given a diagram. It says figure 4 shows a sketch of part of the curve C. The region R shown shaded in figure 4 is bounded by the curve C, the x-axis, and the line with equation x equals 3. Show that the exact value of R is A log 2 plus B log 3, where A and B are rational constants to be found. We're going to be using integration to find this area, and I guess what makes this difficult is firstly having to integrate this expression here, or this equation, and then there's going to be some tricky work with logs as well towards the end. But let's get started on part B. Let's firstly write out the expression we're working with again. So we've got y equal to 15 take 3x, because now we know that 15 equals p equals 15, and then we've got 2x take 4 multiplied by x plus 3 in the denominator. And I guess the first step is to find the definite integral, what we're going from, so 3 to what, and we can find this by letting y equal to 0. So we could say when y equals 0, all of this equals 0, so 15 take 3x over 2x take 4 multiplied by x plus 3 equals 0, and then, well, obviously the numerator must then equal 0, so we're going to get x equal to 5. So we have a definite integral from 3 to 5, and now we need to go ahead and try to integrate this expression. First thing we're going to have to do is use partial fractions to split this up to make it easier to integrate. So we're looking for the integral of y from 3 to 5, and this is equal to the integral of this expression from 3 to 5. And let's firstly use partial fractions, and this is in terms of x, well, with respect to x. So partial fractions is what we're going to do first, and we would say a over 2x take 4 plus b over x plus 3, so splitting up those denominators, or that denominator, this is equal to 15 take x. Oh, actually, what you could do here is to factorize this numerator. So factorize the 3 out and we get 5 take x. And then you could also write this as 3 multiplied by this integral. So I've done that to make it slightly easier. This is equal to 5 take x all over 2x take 4 multiplied by x plus 3. Okay, so now we need to look for a and b. We can do this by, well, firstly rearranging. So if we were to combine these two fractions here, we would have a times x plus 3 plus b times 2x take 4, and this needs to equal this numerator here, so 5 take x. And then we can find a and b by letting each of these terms equal to 0. So when x equals to -3, this would be 0. So plugging in x equal to -3 here, as I said, this part would be 0. Then we'd have b times -6 take 4 equal to 5 plus 3, which would be 8. And then simplifying this would be -10. Divide the other side by -10, b would equal -8 on 10, which simplifies to -4 on 5. Okay, so we have b, and then to make this expression equal to 0, we could use x equal to 2. So when x equals to 2, this would be 0, so we'd have a times x plus 3. Sorry, we're plugging in 2 here. So we'd have a times 5 equal to 5 take 2, which would be 3. So therefore a equals 3 on 5. So now we have our partial fractions. We can say that 5 take x all over 2x take 4 times x plus 3 is equal to a over 2x take 4. Well, if a is 3/5, we could write that as 3 over 5 times this, so 3 over 5 times 2x take 4. Plus b was -4 and 5, so actually this would be a negative here. So we've got -4 on 5 times x plus 3.
And here you could actually factorize a fifth out. So we could say this is a fifth times 3 times 2x take 4. You don't have to do this. I think that it simplifies it, but however you like. So now I've got this expression equal to a fifth times 3 on 2x take 4 on x plus 3. Okay, so rather than taking the integral of this, I can take the integral of this expression, and I still have that 3 multiplied by all of this as well. So to rewrite this then, I'm taking the integral of y from 3 to 5. This is the integral of, now I've factorized the fifth out and 3, so this is going to be 3/5 as a constant before the integral that I've factored out. And this is the integral 3 to 5 of 3 on 2x take 4 on x plus 3 with respect to x. And now we have basically the integral of 2 algebraic fractions, which is much easier to do than our previous expression. We can basically just use logs to integrate these. So this is going to equal 3/5 multiplied by the integral of 3 on 2x take 4. We can write as 3 log 2x take 4, and then we need to multiply it by 1 on the coefficient of x. Okay, so that is one of your log laws for integration. So I'll just write that over here. The rule looks like this. When we're taking the integral of 1 on ax plus b, the shortcut is this is 1 over a multiplied by the log of the absolute value of ax plus b. So that's the rule I'm using here. Then to integrate the next term in this expression, we would have negative 4 log x plus 3. And because the coefficient of x there is 1, we don't need to multiply it by any fractions. Okay, so that is my integral, and this is from 3 to 5. And now we essentially just have to simplify. And now this is more complicated than it sounds. So keeping that fraction out the front, we're going to plug in 5 into all of this. So we would have, well, firstly, this half and this 3 I'll write as 3 on 2. And then I have the log of 2 times 5 is 10, take 4 is 6. And then we've got 4 log 5 plus 3 is 8. Okay, so that's the first. That's plugging in 5, and then I need to subtract when I enter in 3. So we'll have, again, 3 on 2 log of 2 times 3 is 6, take 4 is 2. And then subtract 4 log of 3 plus 3 is 6. Okay, so that's my second term there. And then I need to keep simplifying. And here I would probably go back and check what I'm looking for. So I need a log 2 and b log 3. So I need log 2 and log 3. That's going to be important. Currently, I have log 6, log 8, log 2, and log 6. And I need to kind of simplify those down. Well, 8 I know can be written as 2 to the power 3. So I'm going to do that. See, this is where it's getting tricky because you're kind of having to work backwards from the answer here. And I don't think any of this is obvious, by the way. So to get that log 2, I'm going to write this as 2 to the power 3. And also I'll combine like terms. So I'll have this log 6 and this log 6 together. So I've got 3 on 2 log 6, take 4 log 6. Sorry, that's a positive because I have a negative and a negative. So those two negatives there will become a positive. And then I have negative 4 log 2 to the power 3, subtract 3 on 2 log 2. Okay, and this is all still multiplied by 3 on 5. On to the next page. Continue simplifying. So this 1.5 or 3 on 2 log 6 plus 4 log 6, we could write as 5.5 or 11 on 2 log 6. And then when you have the power here, you can bring it down the front. So multiply the coefficient by 3. So this is the log law I'm talking about. We've got log of a to the power b. This is equal to b log a. So bringing that power down, we've got negative 12 log 2 and take 3 on 2 log 2. Okay, continue simplifying. And also here I'm going to do another tricky step. I'm going to split this 6 up into 2 times 3. So this is 3/5 multiplied by 11 on 2 times log of 2 multiplied by 3. And that's going to split up that 6 into log 2 and log 3. And also simplifying this, 12 take 1.5 is 13.5 or 27 on 2 log 2. And now I have that log 2, so I'm happy with that. And I want to split this expression up into log of 2 plus the log of 3. Take 27 on 2 log 2. And now I have 11 on 2 log 2, take 27 on 2 log 2. What was this? This was 5.5, take 13.5. The difference there is 8. So this is going to be negative 8 log 2 plus 11 on 2 log 3. Okay, so finally we have log 2 and log 3 by themselves. Then we can expand that 3/5 out. So 3/5 times negative 8. That's negative 24 on 5 log 2. And then 11 on 2 times 3 on 5. That is 33 on 10 log 3. Okay, so going back to the question, we needed a log 2 plus b log 3, where a and b, for going up and down, where a and b are rational constants. In this case, I have a and b, they're both rational numbers. A is negative 24 on 5 and b is 33 on 10. A lot of work there, and for sure there are different ways to approach that question. Just a quick rundown again. So we firstly found the upper limit of the area, and then we used partial fractions to split that expression up into 2 parts, and then we took the integral of those using 1 on ax plus b equals 1 on a log ax plus b. And then we had log 6 and log 8, and we had to find a way to create log 2 and log 3 out of those. So we used 2 to the power 3 for log 8, and we used the fact that 6 is 2 times 3 to get log 2 and log 3, and then we kept simplifying. So I used once I found the integral, that wasn't very difficult once we had the partial fractions, but I used 1, 2, 3, 4, 5, 6, 7 lines of working to get to my final answer. Maybe there is a more efficient way to do it, I'm not sure. But there you go, that was my answer for part B for question 13. Total of 11 marks for that question.
Question 14 says the curve C in the standard Cartesian plane is defined by the equation x equals 4 sine 2y, where y is between negative pi and 4 and pi and 4. The curve C passes through the origin O, and part A says find the value of dy on dx at the origin. So we need to go ahead and differentiate this. We could find dx on dy and then the reciprocal of that. So we're given x equal to 4 sine of 2y. The derivative of this, dx on dy, will be, just the derivative of sine, which is cosine. Well, we also need to use the chain rule there, so we will have 4 multiplied by cosine of 2y multiplied by the derivative of 2y, which is 2. So all up we end up with 4 times 2 is 8 cosine 2y. Therefore dy and dx is going to be the reciprocal of this, so 1 on 8 cosine 2y. And you can also do that using the double angle formula and then the product rule. That would still work out. But anyways, we need to find the value of dy and dx at the origin. So when y equals 0, we would have cosine of 0, right? Plugging 0 in there, we'd have
2 times 0 is 0, cosine of 0, and that is 1. So dy on dx would evaluate to 1 over 8 times 1, which is just 1 on 8. So the derivative at the origin is 1 on 8. That's part A. Part B says use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. And part 2 says explain the relationship between the answers to A and B, part 1. The small angle approximation formulas are in your formula booklet, and the one for sine is sine theta is equal to theta for small angles. So if we have a sine of 2y, then this will equal 2y for small angles. So for part B, part 1, we're going to say, well, firstly, let's start off with this equation. We've got x equal to 4 sine 2y, and we're saying that sine of 2y is approximately 2y for small angles. So plugging 2y in for sine 2y, we would have x approximately equal to 8y. Then let's go back. We need to find a relationship between A and B part 1. So we could also rearrange this for, actually let's go on to the next page. So for part 2, we have x equal to 8y, therefore it follows that y is equal to 1 on 8x. So we have then a gradient around the origin, where y is small, of 1 on 8. And we also found that at the origin, the gradient of this curve is 1 on 8. So that would be my general answer to part B, part 2. The fact that dy on dx in A is the gradient of the line in B part 1. Just to expand on that a little bit, if we just try to picture this, maybe that helps it to make a little bit more sense. So we're talking about some curve. Let's say it's going like this. I don't know what it looks like, but let's just assume it looks like this. And if we zoomed in on the origin here, we're saying it approximates a straight line, and the gradient is 1 on 8. And that's what this equation is telling us. The points around the origin approximate a straight line with a gradient 1 on 8. Also, when we take the derivative, the tangent at those points is 1 on 8. Okay, so just expanding on that question a little bit. And then part C says show that for all points x, y lying on C, dy and dx equals 1 over a root b take x squared, where a and b are constants to be found. I'm going to go through two methods for this question. One is more complicated, but it does not involve having to know the derivative of inverse sine or arc sine. So going through the more complicated version first, we know that x equals 4 sine of 2y, and also dy on dx equals 1 over 8 sine 2y. Then we could rearrange this equation to x on 4 equal to sine of 2y. And then you need to see that you need to square both sides. So x on 4 all squared equals sine squared of 2y. And then you also need to know that cosine, or you need to see that cosine squared of 2y is equal to 1 take sine squared 2y. And then cosine of 2y is equal to the square root of 1 take sine squared 2y. Connecting all these things together, oh, by the way, I've written this wrong. This was cosine 2y, wasn't it? So this was 1 on 8 cosine 2y. Apologies. So connecting all these things together then, we can say that 1 on 8 cosine 2y, plugging this in, this is going to be 1 over 8, the square root of 1 take sine squared 2y. And then we know that sine squared 2y is x on 4 squared. So plugging that in then, we have 1 over 8 times the square root of 1 take x on 4 all squared. Okay, so we had effectively there, to get to that point, I had to rearrange that equation remember this identity, which is not really a common one, especially if you're talking about a trig function with 2y in it. It complicates a little bit because there's other things you could do with that function. So to see that you need to do this is complicated. And then we start with the derivative. So this was kind of the third step that I've taken just to get here, and I still haven't ended up with the expression in the form they want me to. So I need to continue to work with this, and this is not straightforward algebra either. So I need to rearrange this expression in here. I've got 8 multiplied by 1 take x on 16, squaring both of those, so x squared on 16. I'll just look at this expression here, 1 take x squared on 16. If I want to simplify this, well, find the common denominator at 16, so this would be 16 take x squared on 16. And then if we're taking the square root of all this, take the square root of 16 in the denominator, this would be 16 take x squared in the numerator over 4. And then if I plug that in here, this would equal 1 over 8 multiplied by the square root of 16 take x squared on 4. That 8 divided by 4 would be 2, so this simplifies to 1 over 2 root 16 take x squared. And that is in the form they wanted us to have it, so a would be 2 and b would be 16. That is the more complicated version, not using the derivative of the arcsine function. So let me go through the method if you do use the derivative of the arcsine function. So we started with, well, let's say this is C method 2. We started with x equal to 4 sine of 2y, and we're looking for dy and dx, remember, so let's find this in terms of y. We would have 2y equal to divide by 4, take the inverse sign, this would be inverse sine of x on 4, and then y is equal to a half multiplied by the inverse sine of x on 4, and then you need to know the derivative of the inverse sine or arcsine, and that is in the formula booklet. I believe it is in the further maths section. Let's just take a look. Yes, so this is under AS further mathematics, so it is down here. So the derivative of arcsine is 1 over square root of 1 take x squared. Now this also doesn't account for the chain rule. If you have a function in here inside the sine function, you have to use the chain rule as well. So for the derivative of this, we're going to have dy and dx equal to a half. That constant we can effectively ignore. For this arcsine, we'll have 1 over the square root of 1 take x on 4 all squared multiplied by the derivative of x on 4, which is a quarter. And then if I simplify this expression, we end up with 1 over 2 times 4 is 8 root 1 take x on 4 all squared, and you're at that point here basically. So rather than having to do all of this, connecting all of those details, we just had to take the derivative of arcsine. So that is the second method. I believe it's simpler, but it does involve having to know that derivative. So there you go. There are 2 methods for part C for question 14. And I didn't finish this off, but because I did that in the first method. So the same, you'd finish that off the same way I did here. Okay, so that was part C for question 14. Total of 7 marks there. And that is the end of the paper. I hope you found that useful. Please leave a like if you did, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.